It's my great pleasure to substitute for Carsten today to introduce the speaker in the TRR seminar, who's Roland Welter, PhD postdoc in the subproject M7 of the TRR. And just very briefly, Roland did his PhD in mathematics analysis of PDEs at the University of Boston in 2021. And then in the fall, joined the University of Hamburg, where he's been ever since in this project. It's kind of varying roles in a way, so good 2.5 years. And well, we're hearing today, I guess, about some of the results of this project work. And please.
Yes, thanks, Jens. Yes, so the occasion today is that I just recently submitted this paper, which I was working on for a long time. And so I wanted to share some of the results. Hopefully they're useful for this climate applied group. So first I wanted to give a little context of some background from where this paper came. And yeah, this was developed in the M7 project. And so here we are, Jens, Camilla, Ivan, Luby, and myself. And so our group has had as a centerpiece this Rayleigh-Benard convection for our studies. Here we're trying to model the planetary boundary layer, or convection within the planetary boundary layer. And we've been using the Boussinesq equations as an approximation, simplified model, which these Boussinesq equations neglect moisture effects and also the entrainment boundary at the top of the planetary boundary layer. But the key aspect is that they're non-hydrostatic, and they don't involve a parameterization in the same way that many climate models do. So we're trying to study without parameterization to try to test these parameterizations that are used. Mathematically, this means that we're solving the Navier-Stokes equations in this domain, coupled to an advective heat equation via a buoyancy force. And so here we have a picture of what's going on. We have the fluid heated from the bottom and cooled from the top, and this induces a turbulent flow. All of these variables have been non-dimensionalized, so the temperature can be taken at the bottom to be 1 and 0 at the top. And we can see that this model depends on 2 parameters. These are our dimensionless parameters. The first is the Prandtl number, which is the viscosity over thermal conductivity. And this describes what fluid it is that you're modeling. So for air, if you take some typical values, it should be Prandtl around 1. And the other is the Rayleigh number, which measures the applied thermal forces. So due to the very large size, so it depends on the size of the domain by this h cubed. And so because of the large size of the atmospheric boundary layer, we're expecting very large Rayleigh numbers on the order of 10 to the 16. So the Rayleigh number is also a measure of turbulence, so we're expecting very turbulent flows. And our main quantity of interest is the Nusselt number. The Nusselt number is defined as the vertical heat flux or heat transport averaged over the volume and also over infinite time. So this removes some spatial and time dependence, but it still depends on the initial states and also the parameters. And it has a very complicated dependence on these. So there's a lot of open questions about this Nusselt number, especially mathematically, but it's also studied by experimentalists and theoreticians, physicists. But one rather well-known famous result about this Nusselt number is these maximum or these scaling laws, which say that the maximum Nusselt number over all solutions has this bound. It's bounded by some constant times the Rayleigh number to a 5/12 power. And so this can be useful for atmospheric scientists who are using some approximations. If they ever find some heat transport larger than this, then they know this approximation is not representing physical reality. But there's still improvements that could be made. It's not known whether this bound is sharp, and you might have a smaller exponent here. And this could actually be significant because of this large Rayleigh number 10 to the 16. Shaving off a power here would be pretty significant. Okay, so we also need to convert this problem into a computational problem via some discretization. So usually people discretize via finite element methods, but the discretization that I'm focusing on has been this spectral method, where you reduce the system to an ODE model by expanding in a Fourier series and looking at what are the ODE solved by the Fourier coefficients. So if you do this and you only include the largest scale modes, then you end up with the well-known Lorentz 63 system. And if we can plot, I made some plots of what it is exactly that's going on with this approximation. Here we see that by doing this expansion, we've forced the fluid to only move in a kind of constrained way. It can only move along these convection rolls, and we can only have kind of big blobs of temperature. So this is a low resolution model. And then on top here, we have a trajectory in phase space. And so if we watch this evolution, we see the buoyancy, and then we see some balancing occurring, and then now the diffusion really kicks in, and the temperature difference dies out. And eventually, this trajectory at this Rayleigh number settles down onto a fixed point, where we have this plume here, and then the velocity moves. Velocity is constant, so the fluid is kind of constantly overturning at a rate which is exactly matched by the diffusion. And so this is kind of what we mean when we talk about an attractor. So at this low Rayleigh number, there's the attractor is really simple. It's just 3 fixed points, the origin and these two other non-zero fixed points. But we can, as we increase the Rayleigh number in the Lorentz model, we see a kind of new picture emerging. So what's plotted here is in orange, we've got the heat transport value from these fixed point solutions. And for low Rayleigh numbers, these are stable. All trajectories are attracted to these fixed points. So we also have in blue some values of heat transport that were computed from random initial conditions. So we begin somewhere randomly, but we end on the fixed points, and that's what we're seeing here. So the heat transport increases as the Rayleigh number increases, but after some time, these fixed points destabilize, and then we see the well-known Lorentz attractor. And so we now see in orange the fixed points exhibiting some heat transport, and then the stable value of heat transport being less. So in this case, the fluid is kind of chaotically moving around and not transporting heat very well. So this is kind of one major interest of ours, because we have these heat transport bounds which apply to all solutions. So they must be larger than the stable value of heat transport, which is going to be more important for physical simulations, because this is the value that you'll actually observe in the atmosphere. These unstable values are kind of special solutions, which you won't actually see. In fact, the M7 was interested not just in this standard Rayleigh-Benard model, but actually a rotating Rayleigh-Benard model, where we've added a Coriolis force, moved into 3 dimensions. But one kind of restriction that we have going on here is that although we're in 3 dimensions, we want to keep the nice properties of 2-dimensional flows. So we have this restriction that along every slice of this 3rd dimension, the fluid flow is the same. And so some goals for phase 2 were to study generic conditions for the onset of strongly chaotic dynamics. So this was really the area of expertise of Ivan. He's got a lot of insight to chaotic dynamics. And another was, what is the role of rotation in the enhancement of heat flux? So initially we were thinking to try to prove an analogous bound for the Nusselt number, well, I guess this should say maximum, but now including rotation. And this bound we actually weren't able to achieve. So it's still a question. In part because of the departure of Camila, but also because we tried all of the standard methods and realized that obtaining a bound like this would require new methods. So we couldn't just get it for free, or get it easily, I guess. But in our first paper, our joint paper with all of M7, we examined the Lorentz equations in this large Rayleigh regime. And here we made use of an interesting phenomenon that for sufficiently large Rayleigh number, the chaotic attractor collapses down to a periodic attractor. And this had been observed, but we actually proved that this happened. And the way this works is we kind of set the Rayleigh number formally to infinity, and there's a nice limiting system in this case, which we perturbed from to get the bounds, the formulas here. And actually, with these analytical formulas, we can prove that the heat transport exhibits a gap between the stable value and the maximal value. So here we have the Rayleigh number rho. It's this normalized Rayleigh number. And here we have in blue, again, random initial conditions heat transport. And in green, we have the heat transport from the analytical formulas we got. And we can then very well describe the heat transport gap in this regime. So then in this latest paper that I submitted, I wanted to kind of reach from the Lorentz equations more towards the PDE, where we would be capturing more of the physical scenario relevant for climate. And how I did this was generalize this process of this spectral method. So I created a hierarchy of models where the lowest order model is just the Lorentz equations, and then generalized it to arbitrary Fourier truncations. So here we just have one Fourier mode and a small ordinary differential equation. And we represent kind of coarse flows, but then we attach more Fourier modes and get a larger set of ordinary differential equations. We can then represent more complicated flows. And since we've generalized this, we can go as far as we like. We get larger and larger ordinary differential equations, but then can represent more and more complicated flows. So yeah, the ordinary differential equations themselves quickly become very complicated, but I don't actually write these down. I actually just coded it up so that a computer writes down the formulas. And then created some codes which take those formulas and solve the equations and visualize them and all this stuff. The kind of key step, though, was how do we choose these Fourier modes? If we just attach them arbitrarily, or how are we choosing them? And here is where maybe the ethos of the TRR comes in. So if you analyze the PDE, you can do some kind of calculus to determine that the PDE implies these energetic balances. So the first here is a kinetic energy balance, where the time derivative of the kinetic energy is equal to the viscous dissipation plus this forcing buoyancy thermal forcing term. And then the next one here is a potential energy term, and this is a vorticity term, and there's some other balances. And now the trick is that if we just include Fourier modes arbitrarily, then the ODE models don't solve these same balances. So I, kind of following some works of others, was able to develop some criteria that if your choice of Fourier modes satisfies these criteria, then in fact the ordinary differential equations do have this energetic consistency with the PDE. So this was how this hierarchy was made. And so then we can take a little look at some high dimensional. So here we're looking at the 190th HPC model, and well, it should represent some nice realistic fluid flow. I guess sorry about this, but I think the running Zoom and this large PDF at the same time is slowed down my computer. But yeah, so we can see that this has some nice fluid behavior and can represent some turbulence. So what I then did with this hierarchy is try to determine how large of models you need to capture the heat transport of the fluid, of the PDE. And so I ran a bunch of heat transport simulations for a large set of Rayleigh numbers going up to 10 to the 6th, and for rotation numbers up to 1,000. And so here we can see that, so kind of the first thing we can see is that the heat transport depends quite a bit on the model resolution. Easily over, or, you know, probably something like 50% around there. And we see also that kind of all of the models agree for some low Rayleigh numbers, but then they all seem to like level off as the Rayleigh number increases. And the lower dimensional models or lower resolution models level off earlier. So this actually, I think, is when I first just did this for Rayleigh numbers up to 10 to the 6th without really knowing what I would get. And I actually believe that this leveling off effect is not indicative of the PDE. So I think all of these models are failing for these large values of the Rayleigh number because they are showing the same kind of large Rayleigh number behavior that the Lorentz equations did, which the Lorentz equations also level off. And this is due to this large Rayleigh number regime that we studied there. So I then kind of reduced the area, the Rayleigh number that I was studying over, and tried to be quantitative about this required resolution. So here I plotted the in the thick green line is the highest dimensional model, highest resolution model. And then in the thick red lines, I plotted plus or minus 10% from this value. And then on the right here, I've plotted the lowest resolution HKC model, which belongs inside this kind of approximate zone, or good approximation zone. And we see that the dimension increases fairly rapidly with increasing Rayleigh number. Okay, how am I doing on time?
No, you took 25 minutes.
Oh, 25 minutes. Oh, okay. Well, then I can describe this next plot too. So this next plot is a bifurcation diagram of the Nusselt number in a fairly, so it's the 21st HKC model. And I chose this model because it was somewhat high dimensional, but also not so high dimensional that I couldn't make these computations. And I reduced the size of the Rayleigh numbers that I was considering so that this HKC21 model should be a good approximation of the PDE in this range of Rayleigh numbers. And so I plotted a bifurcation diagram where what we do is we start from the origin, and then we just track these fixed point solutions. Fixed point solutions are pretty easy to track as you increase the Rayleigh number, because they're just really simple. They're just fixed points. And what we see here is that the origin, and then I should say, the colors indicate the stability of the fixed points, where red is an unstable fixed point solution and blue is a stable fixed point solution. We also see some purple and orange. Those are, purple is a stable periodic solution and orange is a unstable periodic solution, because we can also track periodic solutions since they're also somewhat easy to track.
In green.
And then in green, we see solutions beginning from random initial conditions. And so kind of what the story is here is that the origin is stable for a very small range of Rayleigh numbers, and then it's unstable, and it's shooting out a lot of other unstable periodic solutions. The first one that it shoots out is stable for a kind of good range of Rayleigh numbers. But the other ones are unstable initially. But what I thought was interesting was that these unstable fixed points emerging from the origin later restabilize by shooting out even more unstable fixed point solutions. And so then what you can get here is that there are multiple stable values of the Nusselt number. And this is then seen in these solutions beginning from random initial conditions. You see that they're kind of switching back and forth between which stable value of the Nusselt number they're attracted to. And this is kind of surprising because the random initial conditions that I chose are not very far away from each other. So you have to have a really good precision to detect which Nusselt number it should be attracted to. And I think that's interesting because I wonder how this can be dealt with if you're parameterizing heat transport and treating it as a subgrid process, because you have to have seemingly have to have knowledge of the subgrid variables to determine which macroscopic heat transport value you end up with. So I'm curious to talk with atmospheric scientists about this. Okay, yes, so this was kind of most of the numerical results that I obtained. I also did some theoretical work to try to support these numerical studies. The first one was existence and uniqueness of solutions, which in fact is already somewhat of an approximation theorem, because we know that then these HKC models should converge to the true solution eventually. The thing is, we don't know like how much resolution it would take from a theorem like this. So the thing that I tried to look into was whether I can prove an existence of inertial manifold. And so if I was able to prove this, then I could make a statement like this, that okay, a given approximation captures the inertial range of the fluid, and so the initial the error made by this approximation decays in time. But this type of theorem is not available for equations of Navier-Stokes type yet. Even legendary mathematicians with long careers can't prove this, so definitely not me. But the theorem that I was able to prove is kind of paralleling existing theorems. And what this says is basically this Hausdorff dimension, which I'll roughly say is the approximate number of Fourier modes you need, satisfies this bound, which is kind of this large constant times a Rayleigh number linear power. So this actually is a quite large bound, so I believe it's not sharp, but it's still interesting. Yeah, so all of the code that I wrote for solving these equations and generating the heat transport and visualizing the flows, I've uploaded to GitHub, so I would be very happy if people used this for some studies. And so then in conclusion, some current work that we're doing, all the work that I've shown was done on my laptop. And so I've kind of been trying to move towards higher resolution and Rayleigh number by working on a supercomputer available at Uni Hamburg. With Maxime, we're working to extend this hierarchy to fully three-dimensional flows. And by using new methods, we might be able to obtain this heat transport bound I mentioned, and also a sharper bound on the Hausdorff dimension. So my future plans, M7 was not continued for phase 3, but I'm going to try to apply for an individual grant and maybe continue these studies in a different way. Okay, yeah, thanks for your attention.
Yeah, thank you very much, Roland. Are there questions from the audience here or there?